Hi everyone. In this talk, I will present the paper Multi-Client Verifiable Computation via Conditional Disclosure of Secrets, and this is a joint work with Rishabh Bhadauria. CDS, Conditional Disclosure of Secrets, is a generalization of secret sharing, where two parties, denoted by Alice and Bob, that share a uniform string R, wish to disclose a secret S to a third party, denoted by Claire. If and only if their respective inputs x1 and x2 satisfy some predicate f. CDS is defined by two encoding algorithms, one for Alice and one for Bob, to respectively compute their messages to Claire. Based on these encodings and the knowledge of x1 and x2, Claire runs a decoding algorithm DEC to extract S. Note that CDS does not maintain the privacy of Alice and Bob's inputs. CDS has introduced in the context of private information retrieval, or PIR, and since then found additional applications in the secret sharing and attribute-based encryption domains. In the past 2 decades, different aspects of CDS have been studied extensively, while exploring its communication complexity, the complexity of the decoder, and its expressibility. Regarding the later aspect, note that garbled circuits imply CDS for any polynomial time function, assuming only one-way functions, and implying communication complexity of order k times c, where c is the size of the computed circuit and k is the security parameter. One of our goals in this work is to reduce this rate. In this work, we explore the observation that for CDS with sufficiently long secrets, the secret can serve as a proof for the fact that the output of f equals 1, meaning that every CDS construction implies an integrity mechanism for the underlying predicate f. And this observation is not new, or previously made by Parno et al. In the context of attribute-based encryption, which is a public key object analog to CDS. So here we exploit this mechanism to demonstrate the usefulness of CDS for designing non-interactive two-client verifiable protocols in the presence of an untrusted server, and for a class of predicates that admit CDS. In this setting, a set of clients wish to delegate a computation to an untrusted server, where the clients would like to verify the outcome while performing less work than mutually evaluating the function. Typically, in this scenario, security is proven in the presence of a malicious server or any subset of semi-honest clients, where a semi-honest adversary is a benign attacker that follows a protocol's instruction while trying to violate privacy, while the strongest and most realistic attack scenario is a malicious adversary that can follow an arbitrary attack strategy. In addition, the server cannot collude with the client. When given two CDS schemes for F and F bar, one can construct such a verifiable scheme by having the clients forwarding the server the encoding of their inputs within this CDS scheme. The server then replies with the decoded messages. Then from the secrecy of the underlying CDS, the server should not extract both secrets. Also, if the secret is sufficiently random, then the server will only be able to guess the other secret with negligible probability. So our basic two-client model includes 3 parties, 2 clients, Alice and Bob, that have a secret input and access to a shared randomness, and a third untrusted server. Our constructions can be extended for more than 2 clients as well. We prove malicious security in the presence of a single client corruption or the server. And we note that our protocols apply for a concrete class of predicates, while prior work that use garbled circuits techniques apply for all functions. On the other hand, our schemes achieve better rates. So as a warm-up, here's a simple example of CDS for the XOR function. The parties choose random bits from the joint randomness based on their inputs, where Alice uses this bit to mask the secret S. The secret can be reconstructed by Claire only if the two random bits are equal. Note that this CDS is linear and that the encoded messages rate is optimal. Furthermore, the randomness string includes only 2 bits. In this work, we continue exploring the connection between multi-client verifiable computation and CDS in the malicious setting, and show new constructions for a variety of predicates. In order to use a simulation-based definition for our protocols, we extend the security definition of plain CDS to support 2 additional features, privacy and obliviousness, which I will explain more in a couple of slides. Finally, we construct new CDS schemes for checking equality and inequality for 2 large numbers, PSI cardinality, and more. Our schemes have several advantages compared to previous schemes. Specifically, our non-interactive protocols achieve small upload rate, as small as 10, for moderately long strings, meaning the size of polylogarithmic in the security parameter, and rely on one-way functions in Sigma protocols. We also require a simple and more efficiently realizable setup, as our setup only requires a uniform random string. Applying the CDS abstraction for verifiable computation enjoys some qualitative advantages, which I've specified 3 pluses here. First, CDS-based constructions are non-interactive and require only a single message in each direction. Note that reducing the round complexity of secure protocols is an important goal, where non-interactive protocols are particularly attractive. Here, the client can post their encoding of their inputs and go offline, allowing the server to evaluate the function on the inputs and sending a single message to each client. Note that the verification algorithm can be easily also batched, taking the linear combination of many secrets and amortizing away the communication complexity of the server. This batching approach implies an amortized download rate 1, which is much smaller than the rate of prior solutions, where by download rate, we mean the ratio between the size of the predicate's output function, NS, whereas upload rate is the ratio between the input length and the encoded messages. Finally, recall that CDS schemes require common randomness between Alice and Bob, and this can be viewed as a mutual access to a common random string, which is simpler to realize than employing a pre-processing phase that requires correlated randomness and communication, and also sometimes a secret trapdoor. Okay, so recall that CDS does not guarantee privacy of the party's inputs, and the decoding algorithm requires these values in order to extract the secret. So in order to use this object in MPC scenarios, we extend the basic definition, meaning that we define private CDS that implies that only the output of the predicate may be leaked to Claire. This is achieved by decoding the messages from the parties without the knowledge of the inputs X1 and X2. The second extension is denoted by obliviousness, and it implies that nothing is leaked, not even the secret S, meaning that Claire cannot distinct the 2 cases of extracting the secret correctly or failing in doing so. To ensure that the secret is indistinguishable from a random string, the parties apply a PRF function to the secret. These 3 definitions form an hierarchy of definitions and capture additional scenarios that require both privacy and integrity. We design new private and oblivious CDS constructions for several important predicates, and we then establish our verifiable schemes based on these CDS constructions. We introduced two CDS schemes for equality and inequality. Our first scheme uses one-way functions, and the other scheme uses sigma protocols as well. The following scheme achieves obliviousness. Here, the parties create two one-degree polynomials evaluated on their inputs, whereas extraction of the secret is done by taking the difference of the two evaluations. Note that Claire cannot distinguish the two cases of whether it learned the secret or not. For the second scheme, we leverage the special soundness property of sigma protocols, which implies an algorithm that extracts the witness given two transcripts with the same first message and distinct challenges. Informally, a protocol between a prover and a verifier is called a sigma protocol if it is a three-round public coin protocol for proving the validity of an NP relation such that the following three properties are satisfied. Completeness, which means that an honest prover strategy leads to an acceptance. Special soundness, which implies the existence of a witness extractor given two transcripts. And special honest verifier zero knowledge, which implies the existence of a simulator that can simulate the honest verifier's view. In this work, we require the following additional properties. Efficiently samplable, meaning that the underlying NP statement is efficiently samplable with respect to the witness, meaning there exists an efficient algorithm that samples X given the witness W. In addition, we require randomness extraction, meaning we require an extractor that can extract the prover's randomness given the protocol's transcript and the prover's state. We require this property in order to achieve malicious security in the presence of dishonest either Alice or Bob, where an input extractor is required for the corrupted party. A fundamental sigma protocol due to Schnorr that we also use in this work is a proof of knowledge of a discrete log in prime order groups. Note that the two additional properties we require are met by this protocol, where first it is possible to define X given W. It is also possible to extract the prover's randomness R given access to the protocol's transcript and the randomness used by the prover. So our second CDS construction for the equality predicate uses sigma protocols as a platform to compare between two strings in a private manner. Namely, we leverage the PRF evaluations of the parties' inputs as the randomness sources to compute the prover's first message of the sigma protocol and fix the secret as the witness for the corresponding relation. Moreover, the verifier's challenge will be different in the two transcripts. Then only if equality holds, which implies that the first message is identical, it is ensured that Claire can extract the secret due to the special soundness property of the protocol. Note that this scheme achieves a private CDS as Claire cannot conclude any information about the party's inputs due to the privacy of the PRF. Nevertheless, it can conclude the outcome of the predicate since it can tell whether the extractor had succeeded or not. Security of this protocol can be enhanced to the malicious setting by enforcing correct behavior of Alice and Bob based on the verifiability property of the sigma protocol. The protocol for checking inequality is even simpler, since we will fix the first message to be identical for both parties based on their shared randomness, and the challenge will be computed based on the parties' inputs. If equality holds, then the challenge will be distinct and the secret can be extracted. This protocol also maintains the privacy of the parties' inputs as the previous protocol. In this work, we also show that a non-interactive variant of a recent set intersection protocol by Lei et al. Implies a CDS for the cardinality of set intersection based on one-way functions. Private site intersection, or PSI, is an important functionality that gained much attention due to its broad applicability. It is defined by computing the intersection of two or more sets, X, X1, and X2. We show the variant of their protocol by laid out implies two CDS constructions for verifying upper and lower bounds on the intersection size, yielding the exact size of such intersection with rate 3 communication complexity. We note that these CDS techniques can be easily extended to also address set union cardinality, set membership, and small domain range predicates. As above, we extend the security of these schemes to the malicious setting. Prior work on verifiable set operations for the single client setting relies on stronger hardness assumptions, such as strong Diffie-Hellman and extractable collision resistance hash functions, but also achieves stronger properties such as public verifiability and dynamically changing sets. Based on the observation that CDS can be used to design verifiable computation, we can use our CDS constructions for defining verifiable computation for checking equality or inequality and PSI cardinality. We recall that our corruption model supports security in the presence of a malicious server or in the presence of a malicious client, where a client cannot collude with the server. We compare our construction for checking equality between two large numbers to prior work. Note that prior recent schemes are either proven in the semi-honest setting or in the honest majority setting. In contrast, our protocols are applied in the client-server model, where either one of the clients or the server can be maliciously corrupted. We managed to reduce the communication rate into constant, as well as the round complexity, while maintaining a simple setup where the parties have access to a uniform random string. To conclude, I would like to say that CDS is a useful tool for achieving integrity and worth exploring more. It can help in reducing the rate of the communication complexity, and also requires only a simple setup of a uniform string. Thank you for listening.